Now let's take a look at how we translate informal language to formal statements that involve quantifiers. And here's the first example that we are going to work on. There is a smallest positive integer. Okay, let's try to write this using the quantifiers. So now, in other words, there is a smallest positive integer. In other words, I actually can find such integer so that no matter what numbers you're gonna pick, no matter what positive integers, I'll let someone else choose. I guarantee that the positive integer that I found is absolutely smaller than or less than the one that someone else picked, right? So therefore, with that, I'm gonna say, hey, there is a positive integer, and I'm gonna name this integer m, such that no matter what positive integer someone else can pick, so no matter what integer, well, this is a different integer, may be different, so I'm going to use a different letter n. Someone else, I just let someone else to challenge it, just randomly pick. Someone else picks. I guarantee that my m, the integer m, is always less than or equal to n. Now when this happens, definitely this m is the smallest positive integer, right? So first of all, you probably want to make sure that you are able to convert it into meaning like that. The reason is, do you see that there is, that means there exists, right? So therefore I'm going to write this, there is, that means there exists an integer m, so there exists m. Because I say this is a positive integer, I'm gonna say z plus. Well, such that really just come from here, such that no matter what integer that you pick, in other words, for all positive integer that you pick, right? No matter what, what positive integer, I feel like I need to state positive integer. So no matter, that means for all, that means there's no restriction, just for all, and that someone else can pick, I guarantee m is less than or equal to n. So basically, this is what it is. Okay. Now let's look at the second one. There is no smallest positive real number. Sorry, we are going to change that from positive integer to real numbers now. So in other words, just think about this. So like if you on a number line, all the values on the number line, that's real number, right? So in other words, you begin to pick something. Okay, you let someone to pick some number. Say call this number number 1. Okay, and then I can always find another number that's to the left of the number that you pick, which will be smallest. So in other words, no matter what you pick, I can always pick a smaller one. And how do you guarantee that smaller one? I can just say whatever you pick, I subtract that from 1, then that guarantees that there's another one, right? So in other words, you begin to let other, you just pick anyone. I'm going to show you that I can find another one that's smaller, right? So therefore, I'm going to say, so in other words, you let other people to pick any number. So in other words, for all n that other people pick, any other people pick. So I'm gonna say for all n from real number, and I just said that I can always find. That means I can find. When I say find, that means there exists, right? So there exists m. I can always find another one in real number, such that the number I found is always less than the one that you pick, right? Less than the one you pick. So therefore, this is the symbolic form, which is the formal one for this statement, right? Now let's look at one more example in this short video. So some students may learn the precise definition for the limits in calculus, but some students may just talk about the informal definition. So like, let's take a look at this one. So for the informal definition, I am taking this from the Briggs text, the calculus text. The sequence an converges to L provided the terms of an, like the nth term, can be made arbitrarily close to the limit L by taking n sufficiently large. In other words, if you look at enough number of terms, then the term should be very close to the limit L. This is not a very precise one. This is just informal. It's just informal language. And here's the precise one, also taken from the Briggs text. So now sequence an has unique limit L. So in other words, this is basically the limit of an is equal to L, right? If given any tolerance epsilon greater than 0, it is possible to find a positive integer, and this positive integer really depending on the epsilon. So in other words, you just let someone pick an epsilon, you can always find, okay? So therefore, basically that's kind of like there exists because you are able to find. Such that the distance of this the nth term minus L, this difference between the an and the limit L is always smaller than the epsilon that someone else picked. And whenever n is greater than a certain number n, I'm sorry, that the n is actually the positive integer that we can find, okay? So now let's try to translate this into formal language. So here this is simply just limit the sequence of these limits. Oops, I actually do not need this curly braces. So when n is approaching infinity, so this is what the limits notation right there is equal to L. If, okay, if, that's where the if comes in. Now, given any tolerance, so this is where the for all comes in. Just let someone else choose, okay? Just pick whatever epsilon that you want. So for all epsilon greater than 0. So it is possible to find, so that means that you can always find. So there exists n, okay? There exists n. And this n is actually a positive integer, right? So positive integer. That means I want to say positive integer. And such that, that means such that, and this is true. The difference between an and L is less than epsilon. Whenever, that means as long as n is greater than lowercase n, the lowercase n, which is the index of this term, is greater than n, okay, greater than this, the number that you found, you are able to found, okay. So therefore, in other words, such that whenever this happens, that means for all the n that's lowercase n greater than n, so I'm going to say whenever this is happening, so for all n greater than n, then this will be true. So now with that, I'm going to write, so limit an when n approaches infinity is equal to L if for all epsilon greater than 0, there exists n in positive integer from positive integer such that, okay, for all n greater than n, okay, that's where it comes in, this has to be true. The nth term and the limit is very closer than the number that you picked, okay. So therefore this is actually the formal symbolic form of this whole statement.